Alright. Back to it. Had Friday off because I fell asleep early. Yesterday off because it was an inspiration day. But we're back. Mm-hmm. So the primary variable in an expression or in an operation is the one that sign is used. So if we had 3 as the primary minus 2, 3 is being subtracted from, 2 is the subtractee, this would become signed because we're subtracting an unsigned from a sign. So it'd be 3 minus 2, that's fine. But if it's 2 minus 3, this signed becomes unsigned because we're subtracting from an unsigned. So it'd be 2 minus 3, which is negative 1, which wraps around. And this whole wraparound thing is that we have signed. Signed variable is only non-negative, so 0 and up. So if we go from 2 minus 2, 0, cool. 2 minus 1 goes to the highest value that it can have. So if u was signed, we'd be cool because signed variables are just regular integers. Signed integers are standard integers, positive, negative, 0. Okay. Yep, we overflow by getting a value that's outside of its range. We've signed S, unsigned U, and we say is S less than U? Well, okay, so U is our primary. This is our comparison. This is the guy that's receiving the comparison. This is the guy that's being compared. So the master guy, the parent. I don't even know how we even say this. What do they call the master one? Hmm. If it has 1 and 1, the signed is usually converted to an unsigned. Okay, if we assume that, then their sum would be fine, but their difference would not. Okay. Well, it depends on the direction, really. So it sounds like if this is 3 minus 2, it would still be signed. So, okay. Whenever there's a signed and an unsigned, just assume that it goes unsigned mode. Okay. Okay, so we're saying is a sign less than is a sign less than an unsigned? Well, it converts them both to unsigned. So unsigned -1 means it wraps around and is actually the highest value because it's 0, which is the lowest value a signed can have. But then it goes to the maximum that a 4-byte signed integer can have. That's the 4 billion shit, right? Yeah. So it says, oh, this is actually 4 billion. Is it less than 1? No. So what's going to happen is it's going to say 1 is less than -1. Oh, okay. Alright, so don't fuck with unsigned then. So we're passing this guy, this function that returns a void called do something with an unsigned integer parameter. If we pass it a signed parameter, then it probably fucks up. Yeah. If we pass it -1, well, an unsigned can't have -1. -1 isn't unsigned. So we convert it to the, let's see. That's outside the yeah, it's outside the unsigned range, so it wraps around. Yep. So then we say something is something, whatever. We say, in this case, it would just say x is huge, so we'd say it's -1. We could have something here saying there's x, value initialize, or just initialize it as -1, and then we say x is this, we print, and then do something, and it prints what x is. So it'd say x is -1, or received from user -1. Function returns 4 billion whatever. Yep. Which we do. Yeah, because we're not mixing signed and unsigned, we're just doing something outside the range, so. I think we've done this. You'd think automated tools could pick this up though. They would just detect whenever anything that's receiving an unsigned is receiving something outside of the value, then it should give you an out of range error. Tyler error. Ow! Oh, that pimple hurt. Damn. Okay. 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 So, variables and function parameters should probably not be unsigned. Don't mix them. Sizes, okay. Because the size of something can't be -1. Like this thing's length can't be negative. What would that even be? Sounds like it would just be in the opposite direction, but can't be below 0. Something can't be 0 would be nothing. 0 by 0 is nothing. So makes sense. Sizes, dimensions should be signed. Or oh wait, subscripts and sizes should be signed. Even then, yeah, I guess so too. Because if you're doing like the size of a vector, the length of a vector, which you could say is the size, right? And then you subtract something from it. You need to know what the direction of. But if it's unsigned, then this minus this, it'll still give you, it would be like if I had a vector the size of 2 and a vector size of 3, and I subtracted them, then I should get a vector that's smaller magnitude in this direction instead of that direction. But instead what I would get is 2 minus 3. It'd be 4 billion. It would be a giant vector in the same direction. And retards downstairs. Bit manipulation. Okay. Why, just because we don't do subtractions or manipulations to them, maybe? Because, I mean, maybe I would want to do... Maybe it's easier to reference a certain bit using -1 instead of 4 billion, but maybe not. Assuming not... Oh, makes sense. If we're doing bit manipulation... Meaning having better control over memory. Yeah, I mean, it sounds like right here. We can use unsigned just because if we're not using negatives, we're not using signed values, we can get more out of it instead of having to allocate more memory for stuff we're not even going to use, which would be, instead of making it be positive to -2 billion, say, I don't need the -2 billion. I don't need any of these values. So we just put that memory up top somewhere where we actually need it. Instead of just doubling the memory, so now we have even more values we don't need. We have 4 billion, good, that's what we want. But we have -4 billion now. All these values I don't need. Bit manipulation. Oh, okay. Oh yeah, I guess that's true. Because if I choose the -1 index, isn't that the last index of an array? Because the 0 is the first, so the -1 wraps around. So maybe... Yeah, it sounds like arrays... If I think of an array as a function, its parameters are unsigned. So when I pass it -4, it goes -1, -2, -3, -4, and gives me the third from the last 1, 2, 3 index. Yeah, makes sense. Okay. Fixed width integers. Usually 2 bytes, but it could be, but it's usually 4. Well, it could be 2 bytes. It's a minimum, but it's usually 4. Hmm. Yeah, makes sense. Oh, okay. So 32768 is the max for 16 bits, I guess. So it's 768 to -32769. So if we increment it, then it'll overflow if it's only 16. Or, ooh, what even happens then if you overflow by 1, does it wrap around the other way? I don't know how that works. I don't know what it would overflow as. But it's okay if it actually does have the memory. If it has that expanded 32-bit range. Okay. Yep. Yep. Yeah. Yeah. Yep. True. Okay. So, so then we choose specifically the types of integers we're doing. Okay. So by default, int is probably 4 bytes on a system on my architecture. So using ints as default is fine. But in the case where we have a whole bunch, we probably want to make sure that we're using the limited version, the minimum version, just because we're using a whole shit ton. At least where we don't overflow, that's when we use it. So if I'm using a big value, over 32,767, use a 32-bit version. Oh wow, yeah, there's a bunch of different ones, yep. Why isn't it fixed? Yeah, probably because we need it. I mean, it depends on the architecture. I mean, on some that we can deal with small. Oh, it depends on the program too, but also. Would an architecture have lower memory? Ah, we'll figure it out. Here it is. Short answer goes back to C. Leave it open so compilers could pick the size based on the architecture. That way we could use it without worrying. Okay. Oh, you mean because the integral type is either Boolean character or integer? And you mean it sucks not just having, yes, all ints are this, or rather, ints are this, there are no other ints. So to fix it, oh, because integer by default is determined by the compiler upon use. So you wouldn't even know how big unless you do size of each time, or at least once. Assuming that the size of an int, the size of value, return value, is constant and doesn't change with the architecture, then you're cool. But if it does, then that's fucking annoying because you would never know. Is your integer actually big enough to hold the value or not? hair on the wall. Okay, and the desk. Alternate set that are guaranteed to be the same size because of the integer types themselves. They're called fixed width integers. Rather than just using int, you can determine exactly how many bytes you need. 1, 2, 4, 8, signed, unsigned for each. So there's int 8, int 16, or int 8 underscore t, 16 underscore t, 32 underscore t, 64 underscore t, and then are they just u, or is it? Oh, okay. So it's int 8, uint 8, int 64, uint 64. Got it. Okay. Treated like a signed character. Wonder why. Is that because characters only have so many different values? And they're the same size, maybe? God, my nose is fucked up today. And my voice, too. I don't know why. What happened? Woke up just like sick. No bodily aches or anything. No symptoms of sick, just a sore throat. Doesn't hurt too bad when I swallow, though, so it's better than usual. Usual sicknesses. Okay, here's an example. 32. Oh, 32 is big enough. Okay. So there's C standard int for fixed width integers, because it's not within IOStream, which is just input output. Makes sense. Main. Seems like these are sub-libraries within the C standard that we're including. Excuse me. Sorry. Excuse me. So we get from standard integer 32. Which is big enough for the integer. So, okay. Okay. So we'll do what? Oh, wow, it's a big one. Is it the same for 8? What? Oh. So I'm getting the error that's telling me that the value is too large. So if we do 1,000. Oh, still too small. Oh yeah, because int 8's the tiny. So we'll just do 100. Oh wow. Oh. It is treated as a character. Wow, interesting. Okay. Okay, so if we do this, we need C standard integers, we need output, we need an integer from the C standard, so we'll call them int. We need a 32 because we need more than 32,000. We'll call him x, and we'll value initialize him to be 33,000. And then we'll output him, and then end the line without fleshing. Cool. Alright, that's how you do that. So if I did I want to output something. Well, I don't even want to. I'll just do. So I'll do print value, and then we'll pass him 130. Okay, and then we'll include him, which will be include print value.h. That doesn't exist yet. Okay. We'll make print value.h. Cool. I'll stick with the same naming structure. It's fine. Please, just fucking go back. Oh my god. Okay. Alright, so we'll just do, I mean, there's Pragma. And Pragma's good. Just to make sure itself is already, so it's the same shit basically, it sounds like. Pragma once, and it's everything in the file. Instead of it being, isn't it? So do if not defined, print value, then define print value, and if there's yet, cool. And in print value.h, we will have the for declaration for print value. So it'll be a void print value, and it'll be so I'll do include. Do we want to do this? Do we want to include first? So the inclusion issues are when the for declaration, or when the definitions are in multiple spots. So far I haven't seen include be down here. It's always been at the top. So for now we'll just do I even need any? Yeah, include C standard library. Or no. C standard int. Right? Isn't that a one? C standard int. Yes. Cool. And it'll be int 32t. Excuse me. Cool. What? What do you mean? Unexpected type. Include C standard int. Doesn't need. Just test? Yeah, we don't need that. Okay, well, I'll do the C++ file. We'll call him print value. And we'll do he needs if we include that, then it includes this. Oh, but the things inside should already be declaring to make sure that they aren't being included. I think we're fine. Okay. So we'll do void print value. This guy already includes him, which already includes him, so we should be fine. And 32tx. And then we'll do this guy. We'll do that too. I'll put X. Okay. 400 million errors. This guy has the header. And then we'll do print H is already in here. Value.h. Okay, so the H has a bunch of issues. I don't know what they are. If we just do current project, no? Because this is all within one. I don't know. Yeah, it's all one project. Okay. So if I just did that, don't need that, and we just do include IOStream, include C standard int, and then we just do and then we do C is cool. But here, it's not cool. Why? We have C standard int included here. That is weird. I don't know why that is. I mean, we've included what we need to in these guys. If I just remove him for now. Oh, whoops. Oh, wait. Hold on. So we'll say, so it's not doing anything here because this guy hasn't been defined yet. So we say if, yeah, but shouldn't it just be, So shouldn't it be the whole thing? What if we did... That's fine. What if we do... Oh, wait. Isn't it... Why is it cool now? Does it need to be all caps? Oh. It feels like it does need to be all caps. Let me go back to this. Where's the macro action, yo? Hold on. We need header guards. Caps. We do it to the name. Oh, well, okay. So if I instead did it how I was doing it earlier, we said we include all this shit, and then on here we, if not defined, print oh, is it because it's the same identifier and it's wonky? It's because it's the same identifier here. These guys can't be the same. And in this case, this is the header file. Empty character constant. Line 7 and 6. What? Excuse me. Oh, because it's here. Okay. Cool. And we'll do... these guys should be renamed. Okay. Alright, so we need C standard int here. No, we don't, because we already included it before. So here, all we need is print value. Print value doesn't need IOStream. What? Yes, wait, what? Oh. Print value doesn't need IOStream, but this function does. Okay, so we're saying we want to print this big ass value using this function, so we're calling him and passing him this big ass int. And it's at least, well, it's more than an int 16, it's probably int 32. Yeah, it's less than 4 billion, so So we got him. We include the header file in order to get the forward declaration for the function we're trying to call. The header file is only included one time. And we'll do, I think we put this in the beginning, it's just like pragma. Should be fine. And then we include the header file here. That way, if there's some sort of issue between the forward declarations return type and the definitions return type, or the parameters, 2 parameters versus 1 parameter, then we'll get a link error. Rather, that's not the point. The whole point is the compiler error. The whole point is that if the return types differ, we get a compiler error instead of figuring out later, only having a link error. We need IOStream because this function does the printing. The header file only needs to know this, which is already transitively included here because it's in here. So when we include this guy, we're good here. Include him here. Cool. And when we run it, it gives us the big value. And then when we say yeah, that's it. Fuck it. That's fine. That's all I wanted to try. Wanted to try header guards plus the new integers. So what did I find out? Be careful with the freaking conditional preprocessor directives. Be careful with macros. Note that it doesn't work if I'm defining an identifier that I'm already using. So make sure that they're unique. Why was that? It was talking about why they should be unique before too. Can be any here we go. There it is. Okay. Basically just there's an identifier conflict. Okay. So that's big enough. It will always fit within that. What is going on here? You good? Just the glare from the freaking light. Fixed width when we need an integral type has a guaranteed range. Okay. Yeah, to make sure that our values fit. They typically behave like characters. Apparently they do. Due to an oversight, they treat them wrong. They treat them as signed and unsigned characters. So they print characters. So 5065, it prints A, doesn't it? Yep, 5065. We'll discuss what it actually prints and how to ensure it prints that later on. Introduction to type conversion and static cast. Okay. Type conversion, that's cool. After we cover characters, yeah, we need to look at them first to make sense and how they print. The 8-bit fixed width integer types treated like characters instead of integers. The others are not. Okay. Fixed width don't define new types. They're just aliases for existing types with the desired size. Okay, that's cool. I didn't know there was functionality within the language to override what the size is or to specify the size. I guess that's the point. It leaves it up to the compiler, so the compiler by default picks whatever, 16 or 32. But if I overwrite the compiler by specifying it myself, then the compiler doesn't get a chance to do it because it's open-ended. It says, hey, if you don't specify, Mr. Compiler gets it. But he might be wrong. So you can do it. Cool. The implementation gets to determine which existing type is aliased. Okay. For the platform where it's 32, standards 32-bit int will be an alias for int. Where it's instead 16, it will be an alias for long. So if 16 is normal, a long will get you double, which will get you 64 or 32. But if 32 is normal, a long will get you double, which will be 64. Oh. So does it then do that same for 16? It's an alias for signed character because it's the only 8-bit signed integral type. Bool and character are not considered integral type. Wait, hold on. Excuse me. It is the only... Okay. Bool and character are not considered to be signed integral types. This is the case. It will behave like a character. So among the character, Boolean, and integer types, signed character by default is the only 8-bit signed one. If it instead has a specific 8-bit signed integral type, has some other implementation compiler specific, so implementation being the whole thing, compiler and architecture. If it already has a different one, then int will be an alias for that. So the alias determines upon what the architecture or what the implementation has implemented. Okay. Some potential downsides. Not guaranteed to be defined on all architectures. Okay. Yeah, makes sense. Exotic mainframe or embedded things, which don't necessarily have the 8, 16, 32, 64. Oh yeah, we already talked about that. So a times 64 CPU is probably optimized for 64-bit integers. Just because it can process that faster doesn't mean the whole thing can. Oh, just because it can process it faster because it's just already, it was optimized for it. But if we run out of memory in the end or use more memory, then it means that there are more parking spaces that are full, which takes longer to park, even if I'm really good at parking one spot at a time. If there are less spots, doesn't matter how good I am at getting into one spot, because I have to find a spot. Constrained by memory usage rather than CPU. Larger memory footprint may slow it down more than the CPU processing accelerates it. Okay. Fast and least integral types. To help address the above downsides, the downsides being that the characters aren't guaranteed to be that 8-bit integers are treated like characters, and maybe memory optimization issues, meaning that a CPU is optimized for a specific type. To address the above downsides, 2 alternative sets of integers that are guaranteed to exist. Okay. The fast types, there are least and fast. So there are signed and unsigned. the fastest type with the width of whatever. Same as usual, just faster for some reason. For example, the fastest signed integer type that's 32 bits. So it'll figure it out then. So if we're on a compiler that's 64, and we just do fastest, it'll figure out. Wouldn't it just automatically do 64 then? Why do we even need to do fast if we know what it is? If it's 32, we choose fast. Oh, is it just if we don't know what the CPU is, maybe? Fast and least. We'll provide the smallest with a width. Hold on. Fastest, smallest with a width. Oh, because we don't actually know how much memory or how many bits are given to a particular integer. So if we do fastest and we do 32, it could give one that has a lot more memory. Just because maybe it's faster to find big parking spots than small parking spots. Whereas the least will be maybe more memory optimized. And it will find ones that are as close to that as possible. Okay. So we do least 8, least 16, least 32. And we do fast 8, fast 16, fast 32. We do the fastest one that's at least 16. So if it's at least 16 and we're on a 64, it's probably faster to do a 64. So I can choose. Do I want to prioritize memory usage by using only as much as I need for each? Or do I put more into each so that I can get them faster, but maybe take down my entire processing power? So it's easier to find big parking spots. It's harder to find smaller parking spots. In this case, if I have a lot of parking space that's extra, cool, go fast. But if I don't, go small. Go efficient. Speed versus efficiency, I guess. Makes sense. So there's int 16t, but then there's fast 16t, or least 16t. And these are in standard int. Cool. C standard int. Fast types can lead to memory wastage, as their actual size may be larger. Well, duh. That's the whole fucking point of them. Most seriously, because the size of fast least is implementation defined, different behaviors on architectures will they result to different sizes. But yeah, on one, let's see. A fast 16. Oh, but we're doing unsigned. Unsigned fast 16-bit int called sum type. We give him 0, and then we say -1. Oh, the wraparound value will change. Okay, because if we choose fast 16, it could be a 16 if we're on a 16-bit, but I don't think that exists, so it's probably a 32. But it also could be a 64 if we're on a 64-bit. So does the wraparound value of -1 for an unsigned, which goes to the maximum value, does it go to 2,400,000,000? Or does it go to whatever the maximum 64-bit value would be? Oh, God. Yeah, so you have to know what your system is. You got to know what that value is. Or just don't use the unsigned, and then you don't have to worry about this. This is combining two issues here. The unsigned and the fast. The issue isn't the fast, it's the unsigned. I mean, I guess it is the fast, because if we did the unsigned and we knew that we wanted to use it properly, then using fast least is screwing us up because we don't actually know how much memory the value is getting, so we don't know how big the box is. I throw something in there, I don't know. Does it hit here? Does it hit here? No idea. Or rather, it hits here, but is it, how big is the box? We don't even know. Yeah, makes sense. Yep. It seems like fast 16 would never actually be 16. It'd always be 32 or 64 unless you actually have a 16-bit processor. Yep, makes sense. Best practice, avoid fast. Just avoid the extra shit. Avoid fast and least. Because they may exhibit different behaviors on architectures that they resolve to different sizes. Yeah, it makes sense. Best practices for integral types in general. Given the various pros and cons. This. There's a little consensus. Okay, makes sense. It's better to be correct than fast, and better to fail at compile than runtime. 100%. Rather have the program fail. I'd rather have my test tube explode in the lab instead of somebody's fucking mouth when they're taking the chemical. If you need it with a guaranteed range, avoid fast and least, and just use the fixed width. Well, duh. But if you need a specific crazy type of platform, for which a specific width won't compile, you can decide the rest at that point. Meaning, hmm, okay. If it doesn't have the answers and I need to figure out, so I can't do an int 8 for whatever reason, I just have to figure out the other option. Yeah, it's fine. I mean, there's probably another way to specify, maybe. Size T. Oh. Prefer ints when the size doesn't matter. Hmm. Basically, for numbers that are reasonably small, we do ints. But when we need extended range, we can choose int 64 or int 32. For unsigned, when doing bit manipulation or well-defined wraparound behavior is needed. Avoid shorts and longs because short can evaluate to 8, long can evaluate to 32, but short could also be 16 maybe, and long could maybe be 64. It just depends on if you're 64 or if you're a 32-bit processor. Prefer fixed width instead of fast and least, i.e. just figure out what you need and then use that. Unsigned types for holding quantities. Yeah, just do signed. Unless you really have specific needs. Avoid the 8-bit fixed width because it gets treated like a character because it's the only available 8-bit integral type. Hmm. Yeah, don't use the compiler specific shit. Standard size T. Oh, size. What? Okay. We do size of to figure out are we 32 or are we 64? So the size is 4, and we choose int. We pass int and it returns 4. But what type of the int is it? Size of returns a value of type standard size t. So we're passing it maybe the type. Hmm. If we do oops. Oh. Oh, whoops. What? What is it called? Size of int? Yo, what the fuck? Oh, it's not standard. We can just do it. Okay. Okay. So the point is that we create or we instantiate integer x with the value 0. And even before it gets the value 0, it gets some sort of space in memory, some amount of bits. We're returning how many bytes. So 8 times how many, or 8 times less than how many bits it gets. So the bits divided by 8. The quotient of the bits it gets divided by, or the quotient of the bits it gets an 8. What type is the value? Is it 8? Well, okay. Oh, okay. Yeah, because it prints 4. So what is 4? It returns an integer value. What integral type is that? Do we give a fuck? It is an implementation defined, unsigned, because we can't assign negative bits to something. We have to assign some number of bits, whether it's 0 or whatever. Sounds like we can't even do 0 probably. Implementation defined, unsigned integral type. Size t. Size is the type, and it just gives you a fucking number to represent the size of shit. Why the fuck would we care? Guess we'll find out. It's a type def? Yeah, I don't know what that is. 4 bytes. Ow. What the fuck, man? God, I hit my hand so hard on the wall on accident yesterday, or on the door. Oh, it's all like blistered up. Damn. I need water. I'll just keep recording. Go live. It's fine. Do this all at once. I'm done doing the little tiny recording things. I'll just record it once and then stop once I'm done. Uh, I'll do like 2 hour things. That's what I'll do. I'll keep recording for longer periods of time. Just because it's more convenient instead of having to do all these fucking different uploads and naming them and shit. I just want to post what I do. But I want to do it conveniently. We'll do, I'll do 3 hour blocks and then try that. Because it shouldn't take more than 3 hours to upload something. But, excuse me. Maybe 2 hours because on weekdays I'm going to do like 3 hours of, I think 2's probably strat, but 2 might be it. Okay. Okay. It's defined in a number of different headers. If I need to use it, oh, see standard def. Okay. Okay. Why would I need it? Okay. So I use it as a type for a variable. Okay. I do IOStream for the output. How do I, in Visual Studio 2022, what's the shortcut to go to the beginning of my line? What? Oh, it's pretty good. It's not even that bad. Okay. So we'll do C standard definition. How do I, and then what? Surely end is the end of the line, right? That's better. All right. Okay. So we'll do that, and then we're gonna output. What do we want to do here? We have this integer, and we're going to define a size t, and we'll call it size of x. Size of x and we'll define them as size of x. Okay. And then we will output size of x. Okay. Okay, why would I need a size t? 8 bytes? Damn! It's a long. Holy shit. I don't know when I would need to use them. We use it to represent the byte size or length of objects. Instead of just an int? I mean, we're just using a tiny ass number to represent something. I mean, maybe it's important at higher amounts. Let's just assume of objects. So if we have an object and the object is fucking gigantic, excuse me, maybe it makes sense for it to be unsigned. Well, it makes sense for it to be unsigned because it's not going to be wraparound. We're not going to do any calculations with it. We're not going to change it. Okay. So if we need to use it to display the size of something, like, oh, get the size of whatever the fuck, and we could do in the class to get the size of the object, we do get size. We have a public get size of this. It takes no parameters because it's itself, and it returns a size t. It returns a standard size t, and what it does is it runs size of whatever the hell its own name is. So it'll have that. I guess it'll have its own name. Its own name is defined when it's used. So somehow it'll get its own name. It'll get the size of its own name. It does. Yeah, and then output it, and it'll have room for it to be a big ass thing that's greater than 0 or 0. Well, greater than 0. Or 0 if it's not valid, I guess you could check that. Okay. If we use it, include one of the headers. It doesn't see size of does not require a header. Oh. Okay. Oh. Yeah, it's like being able to use integers. Like if I want to create an integer or if it's like using someone's name, I can say it. The program can say it to me, but for me to create one from scratch, I have to actually bust out the book of the crazy ass pirate letters and chicken scratch in order to actually to write the name authentically. So here, sure, the program can spit out 4, but what is the 4? Well, it's a size t, but if I want to make my own size t, I actually have to go in and include the header so that I can access it, because I can't access the type directly. It can spit out types directly, because whatever is doing the spitting out uses the size t, but I can't use it. It's in there, it's just that I can't reference him unless I bring the book out, I guess. Alright. Much like an integer varies depending on the size t also varies in size. It's unsigned at least 16 bits, but on most, it's equivalent to the address width of the application. Address width meaning how many bits are used for the address, the memory addresses of the application. Application being the executable or oh, so yeah, right now it seems like it's only a 16-bit, so it was 16 bits. Okay. Size of returns a value of size t. Why is this optional? Yeah, we already know this, motherfucker. Oh, I can do that. So if we include, well, yeah, because it's a variable with size, and yeah, we can use size of to ask for the size of objects. So we'll do include C standard definition and IO stream for the output. C standard definition is so we can access size T. So we have main. We'll have we'll have a standard size T named Harry. He doesn't get a value right now, and then we will output size of Harry. Yo, just let me fucking build. Okay. And he's an 8-bit. 8-bit size T. An 8-bit unsigned integer. Oh, so I guess it makes sense that he's 8. This is 8-byte. That's 64. We're on a 64-bit system. It's a 64-bit application for Visual Studio. Upper limit on the size of an object. It must be able to return the byte size as a value of size t, meaning it can't be outside of however big size t is. So it's within, in this case, it's within 64 bits. Which is still fucking huge. It's still huge. So it can't be, I don't even know, because 32 is capped at unsigned. What, like 4.5 billion? Something? So what is 64? I don't know. Oh wait, is that right? Or is it 8.5? I don't know. 4.2 might be the right. No, I thought it was 2. Alright, whatever. So, must be able to return it as a value. Therefore, the byte size can be no larger than the largest value that size t can hold. The 20 standard says, constructing a type such that the number of bytes exceeds its representation is ill-formed. Basically, an object should not be so damn big yeah. So if you had a class that when you make an object of it, it is so big that you can't even get the size of it using a size t, it's too big. If it were possible to create it, it would not be able to return it, as it would be outside its range. Okay, thus, creating an object with size larger than the largest value in a size t is invalid and causes a compiler error. Instead of just wraparound, wow. Let's assume that it has a size of 4 bytes. Oh, Yeah, I was right. That's a 32. Hold on. Hmm. So 32 is 2.1. So 64 is, oh my. Centillion? Oh my god. Or pentillion? 18 pentillion? Holy shit. Looking like the US debt. Damn. Oh nice, I can use these. That's good. Okay. This is a 32. And a 32 regular is 2.1, but unsigned it's 4.2 plus. And these are bytes. 4 billion bytes? Oh, I don't know how big that is. Well, isn't it just times 10 to the whatever? So is that giga? Or is that mega? I think tera's 12 or 15. Is mega to the ninth? Micro. Micro. This feels like it's 4 megabytes. One object 4 megabytes big. However, if it was larger, it's too big. Maybe outside the range. Therefore, no object larger could be created. Is that really? Because it says it's ill-formed. Oh, it says constructing a type is ill-formed. We can't even do it? Well, on mine, it was a fucking 8 byte, so it's actually the 18 pentillion. So, wow. It's ill-formed meaning constructing. Constructing meaning the construction function or whatever the hell. There's the constructor and a destructor. When we make something, if the number of bytes in its object representation is too big, it doesn't get formed, and we get a compiler error. We get a compiler error because it can't be represented properly. Therefore, we don't make it. Therefore, we give an error instead. A strict mathematical upper limit on an object size. In practice, the largest is smaller. Oh, in practice, the largest may be even smaller than this amount. Okay. Other limitations. Some compilers create the largest to half. Other factors make sense. Depending on how much existing memory we have, we limit that at runtime. Ah, okay. Yeah, because it was easy to make big shit, but we couldn't even use it yet. Now, cool. Nice. Easy peasy, baby. Holy shit. Really? The Earth is this big? 5 septillion kilograms. It's like 14 septillion pounds. Oh my god. Excuse me. Wow. Really? Yeah, because it's septillion. It's literally 100, more than 1,000 times too big. Holy shit. Yep. That is crazy. So if we do damn. Forgot that it's a big ass number. What? Oh, it's not even that big. What? Oh, because wait, what? So what if we do a double? Yeah, but it's a small number. I don't know why it needs to be a double instead of an int. That's weird. Right? So if we do cool, it just gives an error because we're not using it yet. And we okay. 4 bytes. Oh, it's just because scientific notation automatically has a decimal, and it's thinking, hey, we're taking 5e2, which is 5.0 times 10 to the 2, which is 5 times 100, which is 500, and turning him, oh, sorry, 5.0 times 10 to the 2, which is 5.0 times 100, which is 500.0, and turning him into 500, which means that we are losing the point, which means we are converting a float, a point value, a floating point value, just a decimal value, into a non-floating point value, an integral value, an integer. That is an issue, so we have a warning to treat that as an error. No, sir. So scientific notation automatically uses floats, so we better be learning about floats, bucko. Did we learn about floats here? Yeah. Substitute that motherfucker and turn that bitch into the exponent, yo. It has to. Okay. Just because of regular rounding, yeah. My back is kind of burning, but in like a not bad way. It just feels good sitting here compared to the bed, maybe. It's like it's warming up. That's a weird feeling. Hmm. Hmm. Oh, meaning if we store them as an integer, it just stores 87. But floating point numbers would keep more of the precision. Okay. Convert these to scientific notation and determine how many significant digits. $34.50, so it's 3.450 times E1. Yep. Oh yeah, true. 3.450, so 4 digits, yep. In this case, there's a decimal, so we'll say 1, 2, 3, so 4.000 times 4.000, 4 digits, be negative 3, yep. Or, oh, whoops. So 1.23005, 5 digits, times 10 to the 2. Wait, why did I say 5? Well, okay, 6, whatever. 1.46. 1.46 times 10 to the 3 times 10 to the 5, 3 digits. 1. So 1.46 to the 5, but 9 digits. God damn. 3.45000 times 10 to the 1, 2, 3, 4. We don't because there's a decimal. Yo. Yep. And the 1.46. Oh. But they are significant. So we'll just say 1.46000 to the 5. Pop. Floating points. Okay. Whole numbers, but when we need some precision. And the floats. Interesting. I wonder how big floats can be then. Oh, because the precision of floats is limited, but the magnitude is not. So we could probably do like 4.2 E99. Save that, return that, but what it gets converted to is way larger than any number can actually save. Maybe. All right. So very, very, very large shit. Basically, guys who use scientific notation, or guys with a fractional component. A floating point type variable is a variable that can hold a fractional component. Oh, that makes sense. Oh, wait. Okay, the floating point, the decimal point can float. That is, support a variable number of digits before and after the decimal point. Meaning render significance, or oh, that's what I was thinking. The floating part, it can float. That is, it can support a variable number of digits before and after. Oh, I guess I was just misreading this. Yeah, it can float. This is 4.3200 times 10 to the blah, or whatever. Okay. They're always signed. When writing float point numbers, the decimal separator must be a decimal point. No comma. You're from a shitty country. You have to get used to using a decimal point instead. GG, buddy. Three fundamental data types. Oh, because long is just adding more shit to it, but a double is a float. I see. Seems like it always refers to them as doubles. Let's test this. So we do IO stream for output. And then we do variable X, but then we give it 5 point. We'll just do 5.0. We'll just do 5 point. Return 0. And then we'll do output X. Oops. And end the line without flush. Double. It always says double. I guess it's because it's implementation defined whether or not things are already doubles. How much memory we give stuff at a minimum. I'm on a 64-bit computer, so, or CPU, I guess. So maybe it automatically does that. Sounds like it. A single precision float, a double precision double, and an extended precision long double. C++ does not define the actual size, it defines the minimum size. So, modern architectures, floats are conventionally implemented using one of the floating point formats. Oh, excuse me. float is almost always 4 bytes, so 32. Just so we can get that kind of precision out to that many numbers. And double is almost always 8, or even more. Long double is a strange type. On different platforms, it can vary between 8 and 16. So for some it's 8, some it's 16. Because if you're on a 16, then a double is 8, and then it is, if you're on a 16-bit computer, well, so on some weird platform, a long double could still be 8. Avoid long double. Okay. Sounds like it'd be 4, 8, 12, but IEEE 754 compatible for float and double. Okay. Include limits, print bools are true or false. Oh, okay. We get the numeric limits of the float, and we test, is it IEEE IEC 559, which is, I guess, the same shit as the other. Okay. Let's see what we get. Okay. So we're getting the numeric limits for these different things, and that is within limits. And then within numeric limits, there is some sort of way to test if it is IEC 559. But it's not a function. It's like some other thing. I still don't know what these are. It's like a template, maybe? I don't know. Because if I wanted to test something, like, is true, and it returns a thing, this guy has to return some shit. It is returning some shit. Or it's substituting for some shit. But there aren't any parentheses. Float is always 4 bytes. Double is always 8 bytes usually. Long double varies. Don't use them. Noted. Some definitions. Float, double, long double. When using them, always use at least one decimal place. Okay. Understand that it is a float and not an integer. 5.0. Zero is an integer. 0.0 is a double. Why is it a double and not a float? I don't know. Oh, because it's a double, duh. 5 is an integer. 5.0 is a floating point literal. No suffix means double type by default. F suffix means float type. 0 is an integer, while 0.0 is a double. It's technically a floating point literal, but because the variable is already a double, then it's a double. By default, they default to double. An F suffix is used to denote, well, yeah, I guess so, just so you don't have to automatically declare memory for extra precision. An F suffix, yeah, that's probably why all kinds of games have it so that when you deal damage, it's always point this, that, this, that, this, that, instead of being smaller or less precise. Denote a literal type of float. Always make sure the type of your literals matches the types of the variables. Otherwise, an unnecessary conversion will result, possibly with a loss of precision. Makes sense. Print floating point numbers. Oh. So when we output 5.0, it doesn't know that it's, well, double. So you'd think it would think double automatically. Oh. Okay. So it still does think it's a double, it's just that standard character output kills the 0. Maybe we do something else, printf, or leave it, I don't know. Output 5, so there's a double, there's a floating literal, and then there's scientific notation. Cool. Oh. Oh, so it only says the numbers up until, because this is, well, it says double, so I guess it just goes to the amount of precision that it's able to. It's not like it's a huge number. But it does, it drops off these last 3 significant numbers, digits. Huh. Floating point range. Oh, here we go. Damn. But since this isn't an F or a D, excuse me, this should be, since it doesn't say F, so this should default to a double, which means it should be giving more significant digits, no? Typically 7 if it's a float, sure. But it didn't even do that. It was 6. I'm gonna go to the bathroom. Let's see, is it time? It's 2 hours.